layer perceptrons. Okay. Now, in its simplest form, actually perceptron is a network that can classify linearly separable patterns. Okay. So, the simplest form of neural network that is used for classification of linearly separable patterns. What is meant by linearly separable patterns? That means to say that let us consider a two-dimensional space. Again, I mean our most simplified example, that supposing we have the space as x1 and x2, okay, two input perceptron let us say, and we have got a set of patterns which are all these things. So, these are the set of one group of patterns, and supposing these are the set of another group of patterns. Now, it is very clearly linearly separable, because we can find one straight line, okay, which is going to distinguish between these category of patterns, okay, from these ones. Okay. So, they are indeed linearly separable. So, this is a two-dimensional case. We extend it to three dimension. There we should be able to pass a plane that should separate the patterns giving an output of +1 from the patterns that give output of -1. We extend it to dimensions greater than 3, then it becomes a hyperplane that has to separate the -1 patterns from the +1 patterns, right. Now, it was shown by Rosenblatt. Okay. I mean, in fact, Rosenblatt is one of the key researchers, okay, in whose name one can associate the perceptrons, okay, that if you have if you have a linearly separable class of patterns, okay, then a perceptron converges. Now, a perceptron in its simplest form would look like this. Let us say again a two input perceptron. Okay. Let us say that we have got input as x1, x2, the synaptic weights as W1 and W2, because we are considering only one neuron. Okay, that is why I am not putting any other suffix, saying it as W11 and W12, there is only one neuron, okay, and naturally there will be some bias, okay, which will be there, bias B, and there will be an output, and let us say that it is giving us a activation of plus and -1. Okay. Now, let us consider some very small examples. Okay. Let us say that we are going to realize an AND gate out of it. AND gate means that in a two dimensional space, x1 here, x2 here, when x1 and x2 both are going to be 0, then the output will be equal to 0, or if we take the activations to be +1 and -1, okay, then we should say that it should lead to -1, okay. Or let us say that why to consider plus -1? Let us say that it is 1 or 0. That means to say that if it exceeds a threshold, it is equal to 1, greater than or equal to threshold, it is equal to 1, and if it is less than the threshold, then it is equal to 0. So, when x1 is equal to 0 and x2 is equal to 0, then the output is equal to 0. When x1 is equal to 1 and x2 is equal to 0, then also the output is 0. When x2 is equal to 1 and x 1 is equal to 0, that means to say this point, then also the output is equal to 0, but when x 1 and x 2 both are equal to 1, then the output is going to be 1. Okay. So, this is a different class. So, that is why I indicated by a different color. So, this is the simplest, that is the AND function that we can consider. Now, is it a linearly separable pattern? Yes. Very clearly, because we can consider a line like this, okay, which is going to separate the patterns giving response equal to 0 from those patterns which are giving response equal to 1. So, this is a linearly separable, and naturally we can solve this problem, okay, using a 2 input perceptron can solve this problem. Let us take OR function, okay, again using the same model. OR function means that when we have x 1 and x 2 both equal to 0, output is 0, but for all the other 3 cases we will be having 1, 1, and with x 1 x 2 both equal to 1 also the output will be equal to 1. In this case, is the problem linearly separable? Very clearly yes. We can find a line that distinguishes the 0 patterns from the 1 patterns. So, this is OR function, okay, and this is linearly separable, and we can solve this very easily using a 2 input perceptron. Okay. Now, let us take an XOR function. XOR function means what? Again take the x1 x2 axis, okay, with x1 and x2 both equal to 0, the output is equal to 0. When x1 is equal to 1 and x2 is equal to 0, output is 1. When x1 is equal to 0, x2 is equal to 1, output is 1, and when both of them are equal to 0, then the output is equal to 0, right. So, this is 0. Now, is this linearly separable? Why? You can't pass a straight line that distinguishes the 1 patterns from the 0 patterns. Okay? I can try to think of any number of straight line, not this one, not this one, not this one. None of the straight lines would be able to clearly distinguish that on I mean one side of the line we will be having 0 patterns, one side of the line 1 patterns, it is never possible. So, XOR problem is not linearly separable. So, we cannot solve this problem using a 2 input perceptron. Okay. We have to do something else. I mean 2 input perceptron, or rather to say I mean even if we extend this XOR to multi dimensions, okay, still since it is not linearly separable, it is not possible for us I mean to form a solution out of perceptron. There we need actually the multi-layered connections. Okay. But more about that later on. Okay. Now, let us go somewhat into the theory of the perceptrons, because we once made a statement that it was shown by Rosenblatt, okay, that if you can find linearly separable class of patterns, if you train a perceptron, a single layer perceptron with linearly separable patterns, then it converges. Okay. I mean ultimately it should be able to, I mean in an m dimensional space, ultimately it will be able to find the hyperplane that separates the 1 patterns from the 0 patterns. Okay. So, convergence he says is guaranteed. Okay. But let us go over to that convergence theory. So, in order to go into the convergence theory, let us consider the unconstrained optimization techniques. Okay. because ultimately we have to see that at what point it leads to the minimum error. Okay. So, it is the unconstrained optimization through which we will try to explain the convergence aspects. Okay. Now, when we train a network, okay, naturally what we are measuring is that we are finding out the difference between the actual response, okay, from what the target response says, because in a training pattern we are feeding the inputs as well as the target output, right. So, the difference that exists between the target output and the actual output, that is the error, okay. And we are taking some measure of the error, maybe the sum of squares and things like that, okay, which will give us some error cost function, and naturally our objective will be to minimize that cost function. Okay. In fact, we had discussed that I mean in our in initial series of lectures itself we had discussed about that, but we will just formulate it more into an integrated theory. Okay. Now, let us consider a cost function. Okay. Consider a cost function. Now, cost function is obviously a function of the free parameters. So, if we call the cost function C, we should write as an argument of C the W vector, the weight vector or the free parameter vector, whatever you call. And let us consider also that this cost function is continuously differentiable. This is very important, that the cost function that we consider as CW is continuously differentiable with respect to the W vector. Okay. In fact, if it is not continuously differentiable, then it leads to a problem. I mean, then we have problem in adopting any steepest descent approach or any other optimization approach, okay, if it is not continuously differentiable. So, that is the basic assumption, that whatever cost function we consider is indeed continuously differentiable. So, what our objective is to find, so our objective, okay, is to find an optimal solution. Find an optimal solution of what? Because we are going to adjust what? We are going to adjust the weights, that means to say this W is something that we are going to adjust. So, optimal solution we are going to find such that, let us say that we arrive at some weight W star. Okay. Let us say that we have found out some weight W star, okay, such that C of W star is less than or equal to C of W. Okay. If we can have that, then we can say that the C W star is the optimal cost, or rather W star, that is the argument of this C W star, that W star is going to be the optimal weight, okay, which we are going to achieve, right. Now, what is the necessary condition of that? The naturally we are not considering any oversimplified case. We should consider now a very general case, that this W will be typically an m dimensional vector, all right. So, in terms of any m dimensional vector also, we should say that its gradient in the multidimensional space, its gradient at that point should be equal to 0. So, that means to say that if we take the gradient of this cost function, okay, that should lead to 0, if this is the point of optimality. If CW is the minimum cost that we can find out from this system, then the necessary condition for that is grad of CW is equal to 0, CW star. So, this is the necessary condition. Okay. Where what is the gradient operator? The gradient operator will be defined as del del W1, del del W2 up to del del Wm, where we are considering m dimensional vector, and because we are writing it as a row vector now, we just indicate it with a transpose. So, this is the gradient operator. So, that means to say that when we talk of grad C, okay, grad C, I mean I am just not writing this W every time, then we are talking of grad C as this vector dou C dou W1, dou C dou W2, dou C dou Wm, this transpose. All right. So, the question is that what is it that we are going to find out. So, the approach that we follow for this is the local iterative descent. And by local iterative descent, what we mean is that we start with some initial weight vector assumption W0. Okay. The reason why I am putting I mean as an argument, I am now going to put a number. Okay. That number will indicate the iteration number. So, W0 is the weight that it will have at iteration number 0, that means to say the starting weight or the initial weight. So, this is initial weight, and in fact, in all the cases we are going to have some guess of the initial weight. Okay. In fact, it does not matter, I mean we can have any arbitrary guess, because if the solution I mean if the local iterative descent algorithm works, then with any arbitrary weight combinations also we should ultimately reach the point of minimum. Okay, that is what we are looking for. So, from this, so starting with this W0, we are going to get a sequence of weight vectors, which we are going to write as W1, W2, etc. continues. I mean we do not know that at what point we are going to find out the minimum. I mean ultimately we are going to find the W star somewhere, and if we can find out the W star, that is where we are going to stop. But the question is that what must be ensured for a convergence is that the cost function of W at the n plus 1th iteration, okay, W at n plus iteration, the cost that we are going to get must be less than the cost that we had at the iteration n. Okay. So, if this is valid, then we can say that the network will ultimately converge, or let us hope that network converges. So, I purposefully write the word hope, saying that sometimes our hope may not be fulfilled, okay, and under what condition the hope does not get fulfilled, that also we have to find out. So, now I mean we are talking about the unconstrained optimization. So, we are going to just describe a few standard techniques in order to have the unconstrained optimization. Okay. And what are the standard techniques? Let us go one by one on that. So, the first approach that we had already described in one of the previous lectures is the steepest gradient. So, this time I can go fast, I mean steepest descent. So, this time I can go little fast because the basic theory is already known to you. So, steepest descent, as you know, is traveling in a direction opposite to the gradient vector. Okay. So, you have to travel opposite to the gradient vector, or rather to say we have to travel downhill, okay, because the gradient will be indicated uphill, and that is why we had to travel opposite to that, that is downhill. Okay. And always downhill movement is something about which we should be careful. You know, when we are I mean climbing down a hill, okay, that time if we, I mean we can take two different strategies. One strategy is that we just make our steps so cautious that ultimately we are going to reach the point of minimum, okay, after taking quite a long time, okay, maybe that we will take few hours to reach the point of minimum. The other approach could be is that we start running while traveling downhill, and you know that running downhill is quite risky. I mean, if you can't control your steps, then there is a risk that you will not only reach the, it will go through the point of minima, and you will even overshoot the point of minima and start climbing once again. So, that is something that you have to avoid. So, it is a downhill travel that we have to understand. Anyway, so direction opposite to the gradient vector. Now, what is the gradient vector? Gradient vector I said is del C as a function of W vector, and instead of writing this del C W every time, I am just going to denote it by a new notation G vector. So, G vector is nothing but this gradient vector. So, G vector is one and the same as this, followed. So, accordingly the steepest descent, okay, can be formally described as, the one which we had already discussed, okay, that W at the n plus 1th iteration will be equal to the W at nth iteration minus what, remember? Eta g n, okay, where eta is the learning rate, okay. Remember we discussed this earlier, okay, and somebody said delta. Delta means it is the gradient. Effectively it is the gradient at multiplied by the learning rate, and the learning rate should be typically small. In fact, learning rate typically should be a quantity that we define between 0 and 1. Okay. It is normally defined in terms of a fraction, so that effectively you subtract a small vector from this. Okay. Yes, any question?
Sir, what happens if we get stuck in a local minima?
Yes, we can get stuck in a local minima, and that is one problem that one has to tackle differently. In fact, local minima is tackled by a method which is called as simulated annealing, and we will be discussing about that later on. Okay. In this case, the simplest of assumption that we make is that we are having a convex hypersurface, okay, where a global minima exist. Okay. Now, the weight correction that we are going to apply on this is delta W n, okay, that can be expressed as W, this is the difference of the weight, which can be expressed as W n plus 1 minus W n, okay, which is according to this equation, okay. This is the change in weight, right. Change in weight is simple, at n plus 1th iteration whatever W was there, from that we have to subtract the weight that was there at the nth iteration, and according to this expression W n plus 1 minus W n is equal to minus eta g n. So, we can simply write this one as minus eta g n. Okay. Now, what we have to know, our starting point was that we must know the cost at the n plus 1th iteration. Am I right? That is what we are looking for, isn't it? So, we can express the cost at n plus 1th iteration. Is it possible for us to express the cost at n plus 1th iteration in terms of the cost that we had at nth iteration and in terms of these deltas? It should be possible. Using what? I can hear that somebody is whispering the technique that is to be used. What is it? Can you speak out? Taylor series expansion, that is correct. Okay. People were mentioning about Taylor series, not very confidently, but Okay, I mean it is the Taylor series expansion that we have to carry out for this CWN1. So, we make some Taylor series expansion, we make Taylor series expansion around Wn to approximate Cwn plus 1. So, Cwn plus 1 can now be, I mean simply we make a first order assumption. So, we simply make a first order assumption of Taylor series expansion, so that we can write Cwn plus 1 as Cwn plus, yes, gradient of W, because we are making gradient of I mean we are making Taylor series expansion around Wn. So, the gradient of Wn and what is the gradient of Wn? Gn, that is correct, okay, Gn, and this should be multiplied by, yes, and what is that in this case? The change. What is the change? Delta Wn. Delta Wn is the small change that we are making. So, it is Gn times delta Wn. In fact, delta Wn is a vector, okay, naturally, because W is a vector and you are subtracting the two vectors. So, delta Wn is also a vector, and if we express delta Wn as a column vector, okay, in order to multiply this by Gn, we must express Gn as a row vector. So, that is why the expression that we should write down is that it should be G transpose n, okay, so that ultimately we get the dot product of this G vector G transpose and this delta Wn, okay. So, that should lead to a scalar quantity, okay, that we will add to this Cwn. This is simply that we will get by the first order Taylor series expansion, right, and this is equal to Cwn minus what, because we had already got this delta Wn as eta Gn, is not it, and eta is a scalar quantity. So, eta can be taken out, and then what we have is G transpose n times Gn. And what is G transpose n Gn? Norm of Gn square. So, this is equal to Cwn, okay, minus eta norm of Gn square. This is very clear, is not it, because what you are having, that you are multiplying G transpose with the G vector. So, if the elements of this are G1, G2, G3 etc., and here also G1, G2, G3 etc., you multiply the two, you get G1 square plus G2 square plus G3 square up to Gm square. So, here this is I mean norm of that, okay. So, we get Cwn minus eta Gn square. Now, what we are looking for? We are saying that we must have Cw, I mean with every iteration the cost must decrease, is not it? Now, is it decreasing in this case? Definitely decreasing, because eta by our choice is a quantity that is lying between 0 and 1. So, eta is positive, and what is Gn square? Gn square is also positive, okay. So, this is a positive quantity, so that whatever cost we had at nth iteration, at the n plus 1th iteration, it decreases in the cost, okay. But what about the magnitude part of the cost, okay, because there is one important parameter that plays a role in this, and this is the eta, okay. You make eta too large. So, eta too large leads to what? Yes, I mean it will cross the point of minima and travel further. If you make eta very large, then it will cross the point of minima and it will go beyond that, you will miss the minima, and then again once it comes back to one of the points, okay, it will again try to go in the, I mean negative to the gradient, I mean minus of gradient direction. So, it will again try to go to the minima, and possibly this time also it will cross that point. So, it will followed by overshoots and undershoots. So, if eta is too large, then I mean okay, we will come back to whatever point you have. So, if eta is too large, then it leads to an underdamped case. Okay? Underdamped. So, underdamped means that it is going to have overshoots and undershoots, and I mean in fact it is I mean it may be even oscillatory. So, eta greater than certain value, greater than some value can make it oscillatory. Whereas, if eta is small, okay, in that case the response is going to be, I mean if it is very small, if it is too small or very small, then it is going to be overdamped, and overdamped means okay, you will reach the convergence, okay, you will reach the point of minima, but you will take more number of iterations. Your number of n in order to reach W star will be quite large. Okay, right. So, any question that somebody wanted to ask? Yes, please. Yeah. It is decreasing. It is decreasing. I am not denying on that. Yeah, but thing is that you can I mean if you are taking the mod of that, okay, then you are but okay, so
I think the higher order terms that you neglected
yeah.
might play a role there, sir.
Okay, we will come back to this point, but I mean even going by yes, I mean the higher order terms, yeah, higher order terms definitely come into play. Yes, that's a very correct observation. Yes, that the higher order terms which we had neglected in this process, okay, will play a role in making it unstable. Okay, so that is why it is very important to control this eta. Okay, because if you make eta on the smaller side, okay, then you may increase the number of iterations, but there is no risk of, I mean missing the minima and going into the underdamped case. Okay. Yes.
Are we continuously even changing eta?
No. We are normally keeping eta. I mean actually there are different types of learning philosophies which people adopt during the neural network training. I mean in fact it is good that the question has already come to your mind that whether we are keeping the eta constant throughout. There are some learning strategies in which people consider that to start with they take larger etas, okay, so that initially when you do not have the risk of crossing the minima you travel fast, okay, and as you go more towards the point of minima you gradually decrease the eta. Okay. So, such learning strategies do exist. So, in such kind of strategies it is often easier to control the convergence, okay, if eta is made like that. Okay, but I mean so far let us assume, I mean to start with, okay, let us assume that eta is something which we are keeping as a constant throughout the training process. All right. Now, in this case, what is the picture that we are getting? I mean, what is the representation that we can imagine out of this type of a cost decreasing philosophy? Okay. Again, let us try to visualize the scene, okay, with a simplest two dimensional case. So, let us say that we have got as a free parameter, I mean in fact since we are bothered about the cost as a function of W, we must consider the elements of this W vector, and just as a very simple case we take a perceptron network which is having only two free parameters W1 and W2. All right. Now, the cost that is there, okay, the cost will be obviously a function of W1 and W2, and it may be that for different combinations of W1 and W2, the cost may be the same. That supposing it is a quadratic cost function as we are mostly taking. Okay. In that case, the quadratic cost function would have a contour like this. Supposing, I mean, for n equal to 0, this is the cost contour that we have got, and cost contour means that if we take any point on this contour, then the cost of that is going to be the same. So, this is the cost contour, and never know, I mean, this could be our starting point. This, I mean, if we take this to be our starting point, that means to say that we are starting with W1 equal to 0 and W2 equal to 0, okay, from that point. Okay. Now, for n equal to 1, the cost contour may be like this. For n equal to 2, the cost contour could be like this. For n equal to 3, it may be like this. Like that, ultimately there will be a point where you reach the minima, and that is where you want to go. Okay. Now, in the case of the overdamped, okay, in case of overdamped response, or rather if we control the eta, I mean if we make eta too small so that the response is overdamped, then we will be travelling somewhat like this, that supposing this is our starting point, that means to say with W1 equal to 0 and W2 equal to 0, with n equal to 1 we may reach this point, with n equal to 2 we may reach this point, and supposing this is the point where we want to go. So, with n equal to with the, so ultimately we are going to reach this point of minimum by travelling this way. So, here this is the typical case of overdamped. Now, the response could have been underdamped also, and in that and in case it was underdamped, then what would have happened? In that case it would have travelled in a zigzag fashion. Okay. So, maybe that, yeah. So, here if we take again a two dimensional space W1 and W2, and if these are the contours that we imagine, let us say this is the contour for n equal to 0, for n equal to 1, for n equal to 2, etc., so on. Now, in this case we would have reached, I mean from this point we might have gone here, 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 like this. It would have travelled in a zaggy fashion. Okay. It would have travelled in a zaggy path in order to ultimately reach the point of minimum. Okay. So, here it is a smooth travel, here it is a zaggy travel. So, there are two things in it, but here we may be able to reach faster, okay, as compared to what we have done in the case of overdamped thing. So, this is the simplest form of approach that we take, where we take only the first order assumption. Okay. And by taking first order assumption, we can see that first order assumption obviously guarantees a convergence, no doubt, but because of the negligence of the higher order terms, okay, the presence of eta can play a nasty role. You make eta too large, it can lead to oscillatory or too much of underdamped response, okay, which is something that we do not want. Now, we now discuss about a second methodology of unconstrained optimization, okay, where we do not neglect the second order term. I mean, we consider the second order term of Taylor series expansion also, and that is done using what is called as the Newton's method. Okay. So, using Newton's method, okay, we can follow unconstrained optimization. Okay. So, here the basic idea is to minimize the quadratic approximation of the cost function. So, using a second order Taylor series expansion, around W n. We may write what here, I mean if we calculate the difference of the cost, okay, we express the difference of the cost delta C W n. Okay, delta C means the difference of the cost, and the difference of the cost will be what? C of W n plus 1 minus C of W n. Okay, so this is the cost difference, and this cost difference, in fact, I mean earlier case also it was a cost difference only. Earlier case it was delta C W n, I mean the one that I am writing just now. In the earlier case, delta C W n was C W n plus 1 minus C W n, which was simply the first order term. So, G T n delta W n was the only term that was there in the delta C, but in this case this G T W n will anyway remain, and with that we will be having a second order term, right. So, what is that? So, we can approximate this, I mean again approximation sign will be there, because after all it is again a second order approximation, we are still neglecting the higher order things. So, this can be expressed as the first order term, which is simply G T n delta W n, okay, the earlier expression that we have got, plus the second order term. In fact, the second order term is expressed in this manner. Okay. It is expressed as half of delta W T n, okay, into Hessian matrix H n times delta W n. Okay. So, I will just write down the expression, okay, so that you can easily understand that why this half has come about, and in fact I mean this is a second order derivative that we are taking, is not it? After all, this is a second order derivative, and if we are taking a second order derivative of the quadratic cost function, okay, it can be shown mathematically that ultimately it leads to this. So, I am not going into the derivation part of the mathematics over here, but simply writing down the second order I mean derivatives, second derivatives, okay, by this type of an expression, but the second order derivatives have been embedded in this matrix, where this matrix is called as a Hessian matrix. Okay. In fact, because we are taking the dimension of the network to be m, okay, m is the dimensionality of the network, that means to say m input. So, in this case the Hessian matrix will be of size m by m. So, it will be an m by m Hessian matrix that we are evaluating at W n. So, it is Hessian matrix evaluated at W n. And what is the form of the Hessian matrix? The form of the Hessian matrix will be as follows, that Hessian matrix will be the Laplacian of, or the second derivative of this cost function, okay, and this is expressible as follows: del square C W del W12, right. So, this is the second derivative with respect to W1, okay, because W1 is the first element of the weight vector. So, weight vector is again W1, W2 up to Wm transpose. So, this is the weight vector. So, at first we have to take the second derivative with respect to W1. Okay. What will be the next term? Correct. Del square by del W1 del W2. What is the next term? Yes, del square del square 1 I mean del W 1 del W 3, and the last term will be del square C W del W 1 del W m, because we are considering m by m matrix. Okay. So, this is the first row, and what will be the second row? Correct, W 2 W 1, W 2 W 1, yes. What will be here? Correct, very correct. Here it will be W 2 W 3. Okay. And then the last row will be here, right, W m W 1. W m W 2, and the last term will be right W m square. Right. So, this is the Hessian matrix, right. So, it involves all the second order terms, second order derivative terms, okay. And if you take a second order derivative, okay, then this is what it will result. So, you have a pre-multiplication of the Hessian matrix, in this case is pre-multiplied by W transpose n and is post multiplied by W n. Okay. In fact, this can be easily derived from the matrix theory, that if you are taking the second derivative, this is what results, okay, for the quadratic form of function. Okay. And in this case, okay, I mean this is very important, that if we now take this delta W C n, I mean delta C W n, if we take, then what we are trying to achieve? We are trying to minimize the cost function, isn't it? So, if we now differentiate the delta term with respect to W n, okay, then the change delta C W n will be equal to 0. The change will not happen when this delta W I mean delta C differentiated with respect to W, that becomes equal to 0. Okay. So, if we differentiate this whole expression, delta C is equal to this whole thing, if we now differentiate with respect to W. So, let me put some number to this equation. So, here it is delta C W n equal to this, and we put this as equation number 1, all right. Then differentiating equation number 1 with respect to delta W. So, differentiating we get delta W n, no sorry, differentiating yeah, I mean this is what we have to differentiate, right, yeah, this one. So, this one if you differentiate with respect to delta W n, okay, delta W rather, then what you can expect? You get the GTN terms as this I mean as it is. In fact, I mean if you differentiate this, it will not be the GTN, it will be GN term which will come. Okay. So, the matrix differentiation, I mean I think I will I mean make it more lucid in the next class by presenting the matrix differentiation theory. I mean if you are not attuned with the differentiation that we are carrying out at the moment. If you differentiate this, then the first term will result in Gn, okay, and the second term will result in what? Can anybody guess? The second term will be Hn multiplied by delta Wn, okay. This also can be shown by matrix differentiation. Okay. So, we are differentiating everything with respect to delta W. So, that is what you remember. So, then we get this expression G n plus H n delta W n, okay, and this must be equated to 0. In fact, G n is a vector, H n delta W n, that also leads to a vector, I mean m dimensional vector. So, this 0 that we are writing is going to be a 0 vector, m dimensional 0 vector. So, that is why I am putting the vector notation here, and solving this equation for what? We are going to solve it for delta W n. So, we get delta W n is equal to minus of H inverse n, correct, G n. Okay. So, that means to say, so because we have already got this as delta W n, so we can write W n plus 1 is equal to W n plus delta W n, and that is equal to W n minus H inverse n G n, right. I mean, I simply substitute for this delta W n, I simply substitute the one that we have got. So, this is what we get as this. Okay. Now, again the $1,000,000 question is that, is it really converging? Okay. In fact, it has been shown that Newton's method converges, okay, asymptotically. I mean, in fact, here because we are taking the second order term, okay, the convergence in this case is guaranteed, and it converges asymptotically and without exhibiting any zigzagging behavior. So, Newton's method Okay. Now, for the Newton's method to work, however, one point that should still be noted is that again Newton's method is also not a very guaranteed convergence, because again you are taking second order terms and you are neglecting anything beyond second order. So, naturally this also imposes some condition, and the condition that is imposed is that this H n matrix has to be a positive definite matrix for all n. Now, this is something which should be noted, that when I say that H n has to be positive definite matrix for all n, then it is not really possible for us to guarantee that it will be positive definite for all the iterations. Maybe that we start with a Hessian matrix that is positive definite. So, H 0 we can control, because H 0 is our initial guess, we may be having a control on that, but we never know that ultimately what H n is going to be, because H n is very much dependent upon the I mean iteration that progresses. So, there cannot be any guarantee that H n will be positive definite for every iteration. So, but I mean generally again, I mean this is true that in most of the cases we have that asymptotically convergence is obtained for that. Okay. Now, in the next class we will be discussing about another methodology for the unconstrained optimization, and before we go into that, in fact, we will be dealing, I mean, we will be spending a bit of time with the matrix differentiation theory, so that I mean, if you are having any doubts about the differentiation of these expressions, okay, those doubts can be solved. Okay. Thank you very much.